Hi, my name is Roger Storm, and I'm talking to you from the Glenn Research Center today. We're going to talk about our planet Earth, kind of an important topic for everybody, as this is where we live, and kind of a bit about how we study the Earth, how we here at NASA find out about our planet. People's ideas about our planet and how things work have changed a lot over the years. It used to be you were very concerned with just your local neighborhood. For example, if you put trash out in your backyard, you learned very long that it got pretty smelly and stinky, so you had to figure out how to get trash away from where you live. People used to dump their sewage in rivers until they figured out you got sick drinking the water from the river. So solved it locally with sewers and separate water supplies. It wasn't until recently that we figured the atmosphere is part of that. If we look at a problem people had of smelly gases going up into the atmosphere, their solution was build a big smokestack. Build a big smokestack and then the gases go away. And you're very happy because now it doesn't stink anymore. But people who live about 10 miles away, well, they weren't very happy because now all that smelly stuff came to them. I sort of thought that anything we put in the atmosphere just kind of went away. Our attitude about the Earth changed in 1968, and it changed with this picture taken by Bill Anders when the first time we sent astronauts to the moon. And he took a shot of Earthrise, of the Earth rising over the horizon of the moon. And for the first time in 1968, we saw our planet like it really is, a very, very solitary ball hanging in the darkness and void of space. And people's attitudes changed. This became a very famous picture and started a whole movement. It started a movement called Earth Week. Today we kind of narrowed that down to Earth Day, but people became suddenly very interested in our whole planet, not just a local neighborhood. And thought about, we got to figure out ways to take care of our planet, and to do that you have to know how it works. Now studying the Earth is a hard thing to do, mainly because it's very big. If we look at our planet, it's 8,000 miles across in diameter. That's 8,000 miles. And if you go all the way around the planet, make a trip all the way around, you're talking 24,000 miles. Studying something that big is not easy to do. It's pretty complicated. One of the things you can do when you study something very large is divide the problem into smaller pieces. So if you get smaller pieces, maybe it's easier to study. So we do that with the Earth. We divide it up into smaller pieces. This is an example of one way to do it. This is dividing it up into systems. And systems are the parts that operate on the Earth. For example, the lithosphere. Anybody know what the lithosphere is? Yeah, that's the land. Okay, the dirt and the rock. The biosphere, that one's pretty easy. What's that? Yeah, that's life on the Earth. Plants and animals. The atmosphere, right, that's the sky, the gases around the Earth. The hydrosphere, that's right, that's the water part of the Earth. 3/4 of our surface is water. And the cryosphere is a little harder. Okay, cryosphere, that's all the babies that live on the Earth. Just a joke, sorry. Cryosphere is really everything that's frozen. A large part of our planet is ice, and it's frozen. And scientists studied each part of this. And it turns out, when you start studying the Earth this way, things turn out to get very complicated. For example, the atmosphere affects life on the Earth. It also affects the part that's frozen. It affects the hydrosphere. It affects the lithosphere. If we talk about just the hydrosphere, well, that affects life on Earth, that affects the lithosphere, that affects the atmosphere, and that affects the cryosphere. And scientists soon found out that this got to be a very, very complex thing. Wow, how do you study all of that? Well, studying it is hard if you go to places on the Earth. If we want to study about what's happening in Australia, it used to be you had to go to Australia, or you had to go to South America. A lot of travel was involved to find out what was going on, and you never found out what was happening simultaneously, hardly, because people were in different places, couldn't communicate. Well, NASA kind of solved part of that problem. What we do is we launch satellites. And satellites, here's an example of a group of satellites that go around the Earth, studying the atmosphere. Satellites are pretty cool to use. Because they can see things so much. If we talk about how a satellite works, a satellite orbits the Earth and sweeps its instruments back and forth and back and forth. A satellite like this going 17,500 miles an hour can go around the whole world once in 90 minutes. And then the world turns and it sees another stripe of the Earth. We see the whole Earth twice in one day. And we get lots of data, information about our planet that was very hard to get otherwise. You can take that data, you can put it into a visualization. For example, we have a satellite that looks at chlorophyll, the part of green plants that make it green. When you examine that and put that data together for years and years and years, you get a picture of how the Earth changes with seasons, how it looks greener and then the green goes away when it's wintertime and the green comes back. If you look at an animation of that, I get this started right here. This is India, the Indian Ocean. Look at how the green in India changes with seasons. Look how the green in Africa changes with seasons. It gets greener towards the Sahara Desert, then less green, then more towards the Sahara, less green every season. Notice how much green is in the oceans. Lots of green in the oceans around our planet. Here's the rainforest. Notice in South America, it stays green all year long. But in North America, we see changes. The green in the ocean, those green plants make 90% of our oxygen. We get the idea that most of our oxygen came from like the rainforest, only about 10%. The first 12 inches of the ocean contain most of the green plants that make oxygen on our planet. So we have to learn to take care of that. I mean, oxygen is pretty important, wouldn't you say? So we study our planet. We have satellites going around the Earth. There's probably, well, right now there's over 3,000 satellites orbiting the planet, and only about 550 of them really work. They're machines. They run out of fuel. They go bad. But we have lots of ways of viewing our planet. So let's look at a couple of systems. We're going to talk today about how a few systems affect other systems on our planet and how we learn about how that happens and figure out some things. We're going to start with the atmosphere, the sky. If you go outside and look at the sky, is the sky very big? We'll take a look. If you look at the sky from horizon to horizon, it's huge. Let's get the button here. We'll go to the computer. Really, really big. If you go out in space and look at the sky, here's a view from a satellite, and this bright blue part, that's our atmosphere. That's the sky. That's the air around the Earth. How many miles do you think it is? How thick is it? How many miles to go from the surface of the Earth to outer space? How long? Well, you might be surprised to learn that the thickness of the atmosphere, the distance to outer space, is 62 miles. It's not that far. That's how far you could drive your car in 1 hour. Here's another view if we take a look at over South America. But that bright blue band, that thin little bright blue band, is all that stands between us and death. That's where our oxygen is. If I was going to take my globe, okay, and I grab my globe here, if I was going to take my globe and I was going to model the atmosphere, I would just take a piece of plastic wrap and hold it tightly around my globe. That's how thick the atmosphere is. Do you think something that thin, compared to the whole Earth, has much effect on our planet? Well, it turns out it really does. It has a big effect. Let's look at one of the effects we're seeing from our atmosphere and how it affects other systems. Anybody have any idea where this mountain is located? Take a good look at the picture. There's some clues. Right, I see the giraffe here. This is in Africa. This is Mount Kilimanjaro in the country of Tanzania. It's almost 20,000 feet tall. That's like 4 miles tall. It's the tallest mountain in Africa. It's actually the tallest freestanding mountain in the whole world. It's an old extinct volcano. And here's where it's located. If we take a look at a map, there's the equator, okay? And whoops, we don't need that today. Let's get rid of that. Mount Kilimanjaro turns out to be right here. There's where it's in Tanzania, that blue dot, sorry, the yellow dot. It's almost on the equator. Okay? What do you know? What do you know about the climate of things on the equator? What's the equator like? Right, it's a very warm place. It's the warmest place on Earth. It gets the most direct sunlight of any place on our planet. So when we look at Mount Kilimanjaro, what looks unusual about this picture? Right, there's snow and ice there up on top of the mountain, almost on the equator, which tells you that as you go higher and higher in the atmosphere, what happens? Right, it gets colder because we see the snow and ice. Well, this is sort of an older picture of Mount Kilimanjaro. Let's look at a newer picture of the same mountain. And again, we're still in Africa. There's elephants this time. And you can see there's layers of clouds even below the mountaintop. It's very high. But what do you notice about the mountain up here? What's happened? Yeah, there's a lot less snow and ice. If we look at a satellite picture of Mount Kilimanjaro, this is from one of those satellites, 1993, lots of snow and ice. 2000, much less snow and ice. Well, what has to happen to get less snow and ice? Things have to be getting warmer, right? You warm things up, snow and ice melt. Is this true of just Africa? Well, if we look at other places in the world, okay, for example, if we look out in Oregon at Mount Hood, in 1984, in August, lots of snow and ice on that mountain. Same place in August of 2002, same season, lots less snow and ice. Here's in South America. This is the Uppsala Glacier in Argentina. Old picture, black and white picture, 1928. All of this is a huge glacier coming down in the Andes Mountains. Go to the exact same place. You see mountains in the exact same place in 2004. The glacier is now here. We have a big lake. They call it Lake Argentina. Such a big lake. Boats go out on it. This is, let's see, let's go to here. This is in Canada. 1917, again, an old black and white picture. This is the Athabasca Glacier. There it is coming down out of the mountains. Big, huge tongue of ice, big sheet of ice, many hundreds of feet thick. Same place in 2005. And now there's what's left of the glacier. We get evidence, okay, all over the world that things are melting. Things are melting. Well, this is not a real ice cream truck. That's a sculpture, okay? But things are melting in a lot of places. I mean, polar bears are in trouble because they live on ice. In fact, even worse, Santa Claus is in trouble because the ice to the North Pole's melting. So, scientists think they have a word for this, and you guys probably are aware of it. What do we call it? That's right, we call it global warming. Okay? Our planet's getting hotter. Now, it's not on fire, but things are warming up. We have evidence that things are warming up everywhere. This is some animation of the Earth's average temperature. Okay, and whether you were above the temperature or below it. If you were above average, and this is the year 1885 down here at the bottom, you can see that it's blue. Okay? And yellow or orange is below average. I'm sorry, it's above average. And in that year, in 1885, only Australia and Alaska were kind of above average. Most of the world that year was below average. Watch what happens as we change years. Let me start this moving. There we go. You can see the years change, and as the years change, some places warm up, get more above average, some places get more below average. 1930s, the middle of Africa got warm. It's warm up in Siberia. 1960s, the Earth kind of cools down. Watch what happens when we get about to the year 2000. This goes to 2009, and you can see that in the year 2009, there was hardly any place on Earth that was below normal. Most places were above normal in temperature. Okay? That's one way to represent temperature change. We've only been measuring the real temperature since about the mid-1800s, collecting data. If we graph it, if you make a graph and we look at it this way, well, here's a graph of global temperature, okay, that's changing from 1850 up to the year 2000. And if you look carefully at that, you'll notice that it goes up and down every year. The red line is a 5-year average. And what concerns scientists a lot is what's happening in the last part of the last century, in this part right here. Our temperature is rapidly going up. Now, it's not a huge amount. You guys are probably pretty good at reading graphs, and if we read the graph and come back to where we start here at minus 0.2, below the average, and then we get up here to positive 0.4. If you do the math, what's it going to be? What's the difference? Yeah, the difference is 0.6 degrees. Not a huge change in Celsius, 0.6 degrees, but an alarming change, and we've seen when we look at the information, if you look at the data about melting. Okay, that small change has caused a lot of different things to happen in terms of melting. We can study it back further if we do this. We take ice core samples. Every year when it snows, you can see layers of snow, just like tree rings in glaciers. And we have guys who actually go down and core into that ice. They pull out a plug. You can measure down the lines and know what year you're looking at. And when the ice forms, bubbles get trapped in the ice. So this may be a piece of ice that they can date back to the year 1000. And then you can do some smart things. You can stick a needle into one of these bubbles. Okay? And you can suck out the air. You can draw the air out of the bubble and actually test it. So we know, okay, we can know what the air was like in the year 1000. And they've done this way back and gotten data. And when you do that, when you go way back and get data, let's look at what happens, okay? This is the average temperature we were talking about, and what happens in the air. And again, this is what we talked about, the change in the last 40 years or so, really jumping up. And from core samples, okay, this is a graph of CO2 in the air. Do you know what CO2 is? That's right, it's carbon dioxide. Carbon dioxide is a gas you get whenever you burn something, whether you burn paper or oil or coal or gas or gasoline, you get carbon dioxide. And what's interesting about this graph is that in the last 40 years or so, look at that, it's shot up. And it's shot up the same as the temperature graph. And when scientists see that sort of thing, they say, whoa, what's going on here? Why are those about the same? And they look for information. Say, is this one affecting that one? Or maybe is this one affecting that one? And it turns out that we think the green one, we think that the carbon dioxide is affecting the temperature. It's something that we call a greenhouse effect. It's real interesting to look back and see what's been going on. If we go way back and look at another graph, this is the amount of carbon dioxide, okay, that's this color, and you can see it kind of stays steady. Back to the year 1000, we get about to the mid-1800s, and then it shoots up. If we look at the world's population, about 500 million people till about the year 1850, and that shoots up. Other gases in the atmosphere, like methane, are pretty much steady until we get to that point and they shoot up. What's so special? What's weird? Scientists say, what's going on here, okay, that things change? And the answer is machines. How did you get around if you lived in the year 1400? You used a horse. You used a horse to plow ground, to draw wagons, to ride on. People used horses for thousands of years. And then we invented cars and trucks, and we invented machines to make cars and trucks, and to make the iron, to make the machines. And all those things use fuel. And when you burn fuel, what do you get? Carbon dioxide. So scientists have correlated, or in other words, put together, the idea that by increasing the amount of carbon dioxide in our atmosphere, we've changed our temperature. Temperature's going up. It's called the greenhouse effect. You know what a greenhouse is, right? Okay. Let's take a look at some. Let's take a look here at some greenhouses. These are some greenhouses. Well, not that. Okay, this kind of a greenhouse where we grow plants. Why do we grow plants inside a greenhouse? Why call that a greenhouse at all? It's not green. Yeah, it's because of the plants inside. What's the advantage of growing plants inside a greenhouse that's made of glass? Well, Here's a big greenhouse, and plants can grow because they need sunlight, and glass lets the sunlight in. Sunlight comes through, plants use the sunlight, carbon dioxide from the air and water to make sugars, starches, and we eat those. It also heats the plants up. It heats things up. You know, you get out in the sun, it makes you warmer. Well, the heat comes off at a longer wavelength, and it gets trapped inside. Heat gets trapped inside of greenhouses. Greenhouse acts as an insulator to keep the heat in. So it lets in sunlight, keeps in heat. Our atmosphere does the same thing. It lets in sunlight and it keeps in some heat. When we talk about the amount of sunlight that comes into our atmosphere, our temperature right now averages 57 degrees. And as energy comes from the sun, some of it goes back into outer space. It's reflected off of clouds, it's radiated off the earth. Actually about 35% of it goes back into space. We only keep about 65%. And here's the root of the problem: carbon dioxide. When we put carbon dioxide molecules up in the atmosphere, when we burn things, carbon dioxide will re-radiate some of that heat back down to the earth that normally would have gone out into space. And that means our average temperature is going up. And the more carbon dioxide we burn, or produce by burning, the more we're going to block heat from getting back out into space. And our average temperatures may get, is going to rise. It's going to go up. We saw that from the data on the graph we looked at. We saw that looking at mountains. Our temperature's going up. The main source of carbon dioxide, and you might have guessed from the slide I just popped up, the main source in this country is cars. A car produces carbon dioxide by burning gasoline. And for every 1 mile you drive, you make a pound of carbon dioxide. That's a lot of carbon dioxide, because a car generally drives about 15,000 miles a year. That means that one car is going to make 7.5 tons of carbon dioxide. And there's millions of cars in this country. There's so many cars. If we look at the amount of carbon dioxide in our country, we can see it matches up where people live. In the eastern part of the country and on the west coast is where most of the people live. Denver and Salt Lake City are out here sort of in the middle. Okay, there's Denver, there's Salt Lake City. There's Phoenix down in Arizona. So carbon dioxide, okay? Carbon dioxide is an issue, and it's going to warm things up. What would you think about the answer to this question? Okay. What do you think would happen if we melted all the ice that's on the earth? What would happen? This is a famous statue. This is the Statue of Liberty. And if we melt all the ice on the earth, the oceans are going to rise. In fact, we think that the oceans will rise a lot. This is 315 feet is the height of the Statue of Liberty from the surface of the ocean. Scientists think that oceans will go up, if we melt all the ice, 208 feet. Which means going to visit the Statue of Liberty is going to look like this. In fact, New York City would look like Venice. It's going to be covered in water. All the streets are going to be underwater. Just a tall building sticking out. If we talk about our country, the East Coast, everything here in light blue would be underwater if we melt all the ice. And big cities, okay, are on the coastline. You have Boston and New York City and Philadelphia and Baltimore and Washington, D.C. and Wilmington, and we have Miami and Tampa, and we have New Orleans and Houston. All these places where millions of people live are going to be underwater. Maybe even worse, right here in Orlando, Disney World is going to become SeaWorld. Just a joke. But it's not a joke that we would cover our coasts. Okay? In fact, if we look at the whole United States, you can see that a lot of the country isn't underwater, but the areas on the coastline are. And Florida has disappeared. We look at the whole, I'm sorry, let's come back to me. If we look at, that's pretty serious. In the last century, well, we've gone up a little bit in temperature. The oceans have gone up about 6 feet by the end of this century, maybe. That's not very much. I thought you said 208 feet. Well, that's if all the ice melts. But even 6 feet, that's the storm surge you get from a hurricane. Does a lot of damage to coastlines. And as ice melts, there's less white to reflect sunlight. So it isn't kind of like a straight line graph. Okay? It's an exponential graph. We get more and more melting as more and more ice melts because there's less reflected heat back into the atmosphere. So that's one way that the atmosphere affects the Earth. Okay? The atmosphere is warming up the planet. That's affecting the cryosphere. That's affecting the hydrosphere. Very good. And that affects the lithosphere, the land, by flooding. Let's look at a couple other examples of how the atmosphere affects the Earth. We had one up here of, just real quickly, we have hurricanes. Those happen in the atmosphere. We have tornadoes. Those happen in the atmosphere. Those affect the land quite a bit. Lightning starts fires. You know that lightning hits the Earth about 2 million times every day. And fires are started on the land by lightning. So there's lots of ways. Okay? There's lots of ways that our atmosphere affects our planet, even though it's only 60 miles thick. Let's talk a little bit about water. Since water covers most of the surface of the Earth, all right, let's talk about how water affects the planet. One of the things that you study in school is the water cycle. Let's take a look at the water cycle here. Okay. No, not that water cycle. We want to talk about this water cycle. Where the sun heats the water and evaporates, it goes over the land, cools off, we get precipitation, it rains down on the land, goes back into the ocean, evaporates again, over and over and over again. That's why we call it a cycle. Okay. It's been doing this for millions of years with the same water. Which is interesting, because since it's the same water for millions of years, maybe some of the water you drank this morning was once inside of George Washington, or was maybe peed out by a woolly mammoth in Siberia 10,000 years ago. Because we recycle it, and it's okay. We use it over and over again, and it affects the Earth. Okay, we're going to talk about. Let's talk about this. How water affects the Earth. This is the Gulf of Mexico, and there is a big river that comes in here into the Gulf of Mexico. You may know it right there, the Mississippi River. And you notice the Gulf of Mexico, the waters are nice and blue, but look what happens when it gets into the ocean. All this brown. That is from the water of the river picking up dirt. Picking up dirt and bringing it down into the ocean. Okay? This is what happens. Water carries soil away. And it changes the shape of the Earth. Sometimes does it very rapidly, like in a flood or a landslide, where a whole water lets the soil all of a sudden flow down a hill. Sometimes it does it very slowly, like the Grand Canyon, where water, running through the canyon, picks up sand, picks up grit, and that grinds away at the rock, carves a whole canyon because of the water flowing through it. Okay? Water does this to rocks. It rounds them off. When we see rocks from the moon, they're jagged. They're not rounded. Close up of a piece of moon rock, look at the jagged edges. When the astronauts went there, this stuff stuck to their suits. It was so jagged. Because there's no what? There's no water on the moon. Nothing to cause erosion and change. So water affects the shape of the Earth. Water washes things away. We have erosion. Let's see, something else water has done. And we're going to look at, this is in Japan. And this is a satellite picture taken with an infrared camera. And this is taken in 2011. And you can see the ocean here. Since it's an infrared camera, vegetation is cooler and shows up as red. So all the red parts are where there's forests. And then there's a river. We can see a river coming through here, the Kitakami River. Comes up and goes out into the Atlantic Ocean, Opa Bay. And there are villages here, there are farms, there are other villages where people live down close to the river. Well, out here in the ocean, we had an earthquake. We had a place where the ocean got changed by the land underneath it. So here's the lithosphere changing. We get an earthquake pushing up under the ocean. Makes a big wave, a tsunami. And the big wave comes into shore. And this is what happened after the tsunami came in. All those low areas are now underwater. And when the wave went back out, it washed thousands of things, cars and houses and lots of people back out into sea. Very bad. So the land affected the hydrosphere, the water, and the hydrosphere then came back and affected the land where people live. Hydrosphere affected the cryosphere. This is an ice shelf in Antarctica. Had been stable for hundreds of years. Very thick ice floating on the ocean. And the tsunami, 8,000 miles away, came in, and the water, the amount of water, it wasn't a very huge wave, but it was a big wave, broke off a lot of ice. This ice is about twice the size of the island of Manhattan. It broke off this ice shelf that had been stable for so long by something that happened 8,000 miles away. So there's the hydrosphere affected the cryosphere. Let's take a look at the lithosphere, okay, the land part of the Earth. You wouldn't think that the land would do much. Land just sort of sits there. Okay? But we see some big changes because of the land. Because the land itself, okay, is not solid. The outside's solid, what we call the crust, but inside, okay, inside things are hot. Okay? That rock gets melty and becomes liquidy till in the inside it gets very, very liquidy. We can look at a diagram of that. Let's take a look at a diagram. You can see that there's the surface on the outside, and inside, very, very, very fluid kinds of rock. And we get evidence on the surface that things aren't even solid on the surface. There are big cracks in the surface of the Earth. Okay? We see places where the Earth splits apart. That's kind of interesting. Why would the Earth split apart like that? This is in Alaska in 1963, a huge earthquake. Look how much the road dropped because the Earth's crust changed. Things split. Well, let's take a look. This is some evidence. This shows where earthquakes have happened all around the world. And this is about 25 years of checking, 1963 to 1998, and there were over 350,000 earthquakes that happened in those 25 years. And every black dot, okay, is an earthquake. We're going to have you be a scientist. I want you to be a scientist, okay? And I want you to look at this map and make some observations about what you see in terms of where the black dots are. Okay, can you do that? All right, we'll switch back and take a look. And I'm going to give you a little bit of time here, okay, and let you make some observations. Raise your hand and tell your teachers what you see in terms of where the black dots are. So we can stop the program and get some student comments. Okay, that should have been enough time for comments from you guys. Let's talk about what you thought of. Did you notice that earthquakes are not spread evenly around the world? Some places have a lot, some places have very few. Did you notice that in the oceans there seem to be lines of earthquakes? Did you see that? We can kind of even trace the lines of earthquakes in the ocean. That along coastlines. Did you notice that there's lots of earthquakes on coastlines in places and not on others? If you look at, let's look at something like Antarctica. Let's look at Greenland. Let's try that one. Greenland is up here, hardly any earthquakes. If we talk about Japan, okay, Japan is over here and you can't even see it. It's blocked by dots. There's an earthquake in Japan every day, several every day. When scientists see something like that, they say, wow, that's kind of weird. Why should there be earthquakes in some places and not earthquakes in other places? What is it about the Earth that makes that happen? We can look at the idea that people have, well, if this is the case, maybe the Earth's crust isn't so solid. We see those cracks, okay, and maybe we can talk about the cracks moving around, that our surface isn't the surface we look at or think about, that it's fluid. When we measure the surface, people go out and would have to use things like this called a transit, and they would sight long distance places and make measurements to see if the Earth's surface moves at all. Today we don't have to do this. Today we have 24 satellites orbiting the Earth at about a height of 11,000 miles. And we get information from those satellites as they go around the Earth. Okay? We have places that send up signals to those satellites. And then the signals come back down and we can determine exactly where we are on the Earth. We have places that remotely sense where we are on the Earth, okay, in lots of places. And the satellites are off the Earth, so if things on the Earth move, okay, the satellites don't move. So what happens is people are going to get information about the surface. Would this thing move to a new location if the Earth's surface moves? Well, sure, it's on the surface, but satellites aren't affected by that. We use GPS systems, and that's what this is all about. The GPS systems tell us exactly where we are on the Earth by getting information from those satellites. And we can make maps of how the surface of the Earth changes. This is looking at the country of India, and I'll put a big black X where India is right here. And what we see is that the continent, subcontinent of India, is moving this way. Can you see those blue arrows? And it shoves up and makes the Himalaya mountains. And then it moves, the Earth moves and goes down the Sichuan Basin, goes north towards the Gobi Desert. We can tell that things are moving. This is another place on this. This is in Turkey. And we can see that the country of Turkey, which is right here, okay, things are moving. Okay? Surface of the plates are moving. So the arrows go that way, and then it's moving out into the Mediterranean Sea. Wow. Did you ever feel the Earth move? Have you ever felt the Earth move? I did. I felt an earthquake once. I felt things shake. So that idea about earthquakes and the moving Earth and all this sort of thing, we get an idea that our planet is changing. This is a graphic we're going to look at. It's an animation that shows what we think has happened over many millions of years. We think that our continents used to be all together, and that over millions of years they've moved apart, because we can see today from satellite information that things are slightly moving. And there was a guy named Wegener who looked back in the 1920s and says, hey, it's interesting to look just at the shapes of continents. If you don't think anything else, it looks like South America fits real neatly into Africa. And if we look at, let's see, here's the animation, you can see that it's going to rerun here. We're going to get right there. Look at South America and Africa are moving apart. South America would fit really neatly into where Africa is. And South America and North America are moving more towards Asia. We talk about India. India starts out down here. And India moves northward and crashes into Asia, and that's what's made the Himalaya mountains. You can see Australia moving northward. Australia starts out down here. And it moves east, and then it ends up moving north. Well, that's kind of interesting. Okay. Do you have more information about why that happens or how it happens? Well, there's other things we can look at. We can look at fossils. We can look at where things live, where we find fossils. When we look at where fossils are found, let's switch over here and look at this little guy over here. Let's take some black. This little guy's fossils. Look where we find it. We find him in South America. We find him in Africa. This ugly little thing here, we find him in Africa and India and Antarctica. We find fossilized plants. This plant in Australia and Antarctica and India and Africa, South America. So we think all that land was together at one time and has since moved apart and separated. Where oceans now separated, they were once together. We have this idea, okay? We have this idea that our planet is very fluid. The outside, even though it's solidified, it's cooled off over 4.6 billion years, that the outside has cooled off but still moves because of the insides of the Earth. Let's look inside, okay? Here's inside the Earth, and we think this is what's really happening. Remember the water cycle? Well, we think there's another cycle going on here where things heat up and flow towards the surface from the inside of the Earth, flow out from the middles of the oceans. That's why we saw earthquake lines in the middle of the ocean, because the land is moving apart. Okay? The surface of the land is moving apart from where this flows up from underneath. And flows apart this way, and then eventually you run into a continent. The rock that makes up the bottom of the ocean is denser than the rock that makes up a continent. So when you get to a continent, this gets shoved back down again. Goes back down and melts, comes back up. This goes back down and melts, comes back up. There's our cycle like we saw with the water cycle. We see the same thing with rocks in the earth, melting and rising to the surface, moving and going back down again. Okay. Well, this is very interesting. This explains a lot of things we see. It explains why we see mountains at coastlines, because the ocean bottom is moving over here and going down, and that shoves this part of the crust gets shoved upwards. So we get mountains like the Himalayas. We get mountains like the Andes and the Rocky Mountains. And we get trenches. The bottom, the most deep place of the oceans are where the ocean's floor is diving down. So we get places like this, where there's a big trench, very deep place. And the mid-ocean ridge is spreading out, and that's why we see earthquakes at the mid-ocean ridge. And where these two continents crash together over here, we see earthquakes at the edges of this. In fact, if we look carefully, okay, the edges of the parts that are moving are defined by the earthquakes. If we look at these red lines, that's where the earthquakes were. And that's where the plates are, okay, the major, they call them tectonic plates of the earth that are moving. South America's moving this way, Africa's moving this way, North America's moving that way. And it's at the edges of the plates where these things run together that we see all the earthquakes that happen. Okay. And earthquakes aren't the only thing that happens. Okay. There's something else that happens where plates come together or where plates come apart. And this is what happens. We see volcanoes. Volcanoes are very interesting to study too. Volcanoes are a way that the earth, the land, affects other systems. We talked about affecting other systems. So here's a volcano. We can see the lava coming up into the atmosphere. This is an eruption that happened in 1991 in the Philippine Islands. This was called Mount Pinatubo. It had been sitting there doing nothing for 600 years. Okay, and then movements in the Earth's crust allowed things to blow up. Okay, pressure built up, and rock and gases went up in the atmosphere 20 miles. 200 tons of sulfur dioxide gas got split way up into the atmosphere. And how does that affect the rest of the Earth? Wow. Here's what happened in the Philippines. Gravity brings the rock and dust back down. It got coated, okay, in ash from the volcano. They had to sweep it off their roofs and their cars to keep things from caving in. This is a house. You can see the ash covers everything. Plants, the ground, houses. It's just a mess. At the airport in Manila, so much ash fell on the tail of this airplane, it pushed the tail down. And the nose got stuck up in the air. So they had to push and brush all the ash off the tail of the airplane to get it back on the ground normally. You don't want to be in something like that, okay? It affects the biosphere. It affects the land. We can see that we said it covers plants, but look at the sky. It affects the atmosphere also. It got very dark when this volcano happened. The people in the Philippines went out, and it was as dark as nighttime at noon because the ash blocked out the sun. This is some data from a satellite measuring how clear the atmosphere is. Okay, and before this volcano erupted in Mount Pinatubo, the black and the blue color means the atmosphere was very clear. There wasn't a lot of dust in the atmosphere. This is where the volcano is, right here in the Philippines. And we're going to talk about the United States. The United States, we can take white here. The United States is right over here. There's the United States. So it's on the other side of the globe that this happened. When the volcano erupted, okay, the air was very clear, we said, but If we look 5 weeks later, a little over a month later, the dust had gone clear around our planet, 24,000 miles in 5 weeks. And in 10 weeks, in a little over 2 months, 2.5 months, the dust had spread out clear to the North and South Pole. And this dust went around the world 7 times for 3 years before it settled out. Some of this dust is it's actually in your backyard from the Philippine Islands as it settled out of the atmosphere. Well, if we look at another effect of that, remember we looked at temperatures before? We saw the temperature graph of the Earth. Let's look back at that. And you can see the temperature, like we said, was kind of going up, remember, and rapidly rising since the 1960s. And then look what happened when the volcano went off. What happened to temperature? Yes, it dropped. Temperature dropped because the volcano went off. Isn't that unusual? Why? Scientists say why. So why did that happen? You think of volcanoes, you think of them being lava and things that are hot. But the Earth's temperature went down. Can you think of a reason why that might have happened? Okay. Well, the reason is dust. You're right. The reason is dust. And what happens is this. There's a picture of the atmosphere after the volcano had gone up. And if you look carefully, you can see not one, but 2 layers of dust in the atmosphere. And the effect of the dust in the atmosphere, good old Mr. Sun is shining up here, okay, is that some of the sunlight got reflected back out into space. A lot of it went through. Okay, we didn't freeze, but some of it got reflected back out into space. And that's why, when we look back at our graph, that's why the temperature dropped. It went down a few tenths of a degree because of Mount Pinatubo in the Philippines. And notice it did not stay down. That's something else to look at. Look at it, came back again, went back up. Why do you suppose? Why do you suppose the temperature rose back again? Why did it go back up? Yeah, the dust settled out of the atmosphere. Remember, in 3 years, went around the world 7 times, but eventually it all settles out. And that allows the sunlight to come back through. So here's a case. Here's a case where the land, the lithosphere, the volcano, blew up, threw a lot of stuff up into the atmosphere. The atmosphere carried that around the world, blocked sunlight, and affected the temperature of the cryosphere. Some of that melted because of this. It affected the biosphere, covered things in ash, less sunlight to grow. It affected the hydrosphere, changed the temperature of the oceans. And it affected the lithosphere again, it affected itself, if you will, because dust got spread out and distributed everywhere. So we've had some examples of how one part of the Earth affects the other part of the Earth, and how we use satellites, and that kind of information to study our planet. Hopefully we'll be smart enough to use this data, to use this information to do things better, to do things different. If we don't do something about the amount of carbon dioxide in our air, what's going to happen to our planet? What do we have to do to change that? Well, we've got so many cars, we have to do something different than cars. If you were a scientist in 1850, and you were looking at how the population of the Earth is getting bigger and bigger, you would get very worried. You would think that by the year 2014 that the entire world would be 6 feet deep in horse manure. Because you'd figure, well, there's so many people, it's going to take so many horses, we're going to have way too much manure, we're going to be in serious problems. What happened? Well, the technology changed, didn't it? We don't use horses anymore like we did. We use machines and cars. So maybe we're going to think, wow, if we're going to solve the carbon dioxide problem like we solved the manure problem, temperatures keep going up, we're going to have to change how we do things, how we do business. We're going to have to change our technology about how we get around, about burning less fuel. So if we don't, we're going to melt ourselves into floods and into problems. So maybe you guys will be the ones that will figure out new technologies, how to make solar energy work so we can use it all the time, not just when the sun is shining. How can we store it? How can we take care of it? That's the challenge of the future. That's why you guys are in school today. okay, to learn new things and use that learning to think of new ideas. Thanks for having NASA in your class today. I hope you learned some things about how the Earth interacts and about how we study about the Earth and about some of the challenges we face. You guys have a great day. Study hard, okay? And we'll see you again. Bye-bye.